Warm welcome to yet another discussion on electronics and communication network related papers. Today we are checking GATE 2008. So moving to a 1 mark question. In the following circuit, the switch is closed at t equal to 0. The rate of change of current d by dt of I of 0 plus is given by. So here switch S is closed at t equal to 0. That means before t equal to 0, the switch was open and the current flowing through the inductor is before closing the switch, that is IL0 minus equal to 0. And we know inductor opposes sudden change of current. That means after closing the switch or at the instant of closing the switch, the current flowing through the inductor remains the same, that is 0. And we have to evaluate d by dt of IL0 plus, right? So at the instant of switching or at t equal to 0 plus, all the current flows through this RS, right? So all the current flows through this RS. Therefore, at the instant of switching, that is at t equal to 0 plus, voltage across the inductor, right? Voltage across the inductor equal to the voltage across RS, right? As no current flows through the inductor, it also implies that the serially connected resistor also does not conduct any current, right? So I can write voltage across the inductor is VL0 plus equal to voltage across resistor. Voltage across resistor is IS into RS, as all the current flows through this RS. But we know VL, voltage across inductor, VL0 plus equal to L into di by dt of 0 plus, IL0 plus, right? Now we can equate these two expressions, that is ISRS by L equal to d by dt of IL0 plus, right? Therefore, the rate of change of current is equal to ISRS by L. So option B, right? Option B. Now moving to a 2 mark question. The Thevenin equivalent impedance Z Thevenin between the nodes P and Q in the following circuit is, right? So for calculating Thevenin impedance, we have to deactivate all the sources. For deactivating voltage source, it must be short circuited, and similarly for deactivating current source, it must be open circuited. So I am drawing the equivalent figure here. This is point P, right? This is point P. From point P, there is an inductor. Inductor value is given as 1 Henry. So SL turns out to be S. Now a resistance of 1 ohm and the voltage source is deactivated. That means it is short circuited. Now a capacitance of value 1 farad, right? 1 farad indicate 1 by SC. That means 1 by S, right? So I am marking it as 1 by S. Now another resistance of value 1 ohm and the current source is open circuited. 1 ampere current source is open circuited. So the circuit turns out to be like this. Now we have to calculate the total impedance between the points P and Q. So that is 1 plus 1 by S, right? 1 ohm is in series with 1 by S. So 1 plus 1 by S in parallel with the S plus 1, right? That is S plus 1 plus 1 plus 1 by S divided by S plus 1 plus 1 plus 1 by S. Now I am multiplying both the numerator and denominator by S. That is S square plus 2S plus 1 divided by S square plus again 2S plus 1. So the answer turns out to be 1. So option A is the correct one. Now the driving point impedance of the following network is given by Z of S equal to 0.2 S divided by S square plus 0.1 S plus 2. The component values are, right? So first of all we have to evaluate the driving point impedance. driving point impedance is nothing but it is the impedance faced between these 2 points. So there is an inductor. Inductance impedance is SL. That means SL in parallel with 1 by SC in parallel with R. Right? That is SL in parallel with 1 by SC is SL into 1 by SC. That is L by C divided by SL plus 1 by SC. Right? In parallel with R. Right? That means L divided by, I am multiplying both numerator and denominator by SC. So there is a S also in numerator. Now on denominator side it is S square LC plus 1. Right? In parallel with R. Now taking the parallel combination of these two elements, SLR by S square LC plus 1 divided by SL plus S square LCR plus R, right? Divided by S square LC plus 1. Cancelling S square LC plus 1, we obtain SLR divided by S square LCR plus SL plus R, right? Now checking the expressions, on the denominator side coefficient of S square is just 1. So we have to again divide both numerator and denominator by LCR. That turns LR by LCR. That turns S by C, right? S into 1 by C divided by S square plus S into dividing by LCR. That is S by CR plus 1 by LC. Now we can compare the expressions, right? So on the numerator side 1 by C equal to 0.2. That means C equal to 1 by 0.2. 1 by 0.2 is 5. So 5 farad is the capacitance value. Now we can take 1 by LC. Right, 1 by LC equal to 2 and L equal to 1 by 2C. That means 1 by 10. 1 by 10 is 0.1 Henry. Right. So now finally we can check R also. That means 1 by RC, I am writing here 1 by RC equal to 0.1 implies 1 by 0.1C equal to R, that is R equal to C equal to 5 farad. So 1 by 0.5, that means R equal to 2 ohm. So R equal to 2 ohm, C equal to 5 farad and L equal to 0.1 Henry. Answer turns out to be D, right? D is the correct one. Now moving to another 2-mark question. The circuit shown in the figure is used to charge the capacitor C alternatively from two current sources as indicated. The switches S1 and S2 are mechanically coupled and connected as follows. For 2nt less than or equal to t less than 2n plus 1t, for n equal to 0, 1, 2, S1 to P1 and S2 to P2. Similarly, for 2n plus 1 into t less than or equal to t less than 2n plus 2 into t, n equal to 0, 1, 2. S1 to Q1 and S2 to Q2. Assume that the capacitor has 0 initial charge. Given that u of t is a unit step function, the voltage VCT across the capacitor is given by. So, in the question, being a lengthier question, right? So, in the question, a capacitor is charged in two ways, right? In the first way, the capacitor is charged as in this figure. That means when the switch S1 is moved to P1 and similarly switch S2 is moved to P2. During the first case, the capacitor charges using this 1 ampere, right? This 1 ampere in this way, right? At that time, switch S1 is moved to P1 and similarly switch S2 to P2. But this connection S2 to P2 gives a closed circuit here. S2 to P2 gives a closed circuit here. As there is no return path to this connection, there will not be any current flow during this way, right? Similarly, at the second case, the capacitor charges using this direction. Here also, there is no current flow from this path, right? So, in the first case the capacitor charges using the green color, that means this direction. Similarly, in the second case the capacitor charges using this direction. We have to evaluate the voltage across the capacitor. So coming to the solution, we know capacitor charging discharging expression Vc equal to 1 by C integral I dt. Right? For the time 0 to t, we can take Vc equal to 1 by C integral 0 to t I dt. Right? But capacitance is given as 1 farad. Right? Capacitance is given as 1 farad, and similarly current I equal to 1 ampere. Right, a current as 1 ampere. Now Vc turns out to be, the capacitor voltage turns out to be integral 0 to t I dt. Right, that is integral 0 to t I dt equal to t. So now we obtain the capacitor voltage for 0 less than t less than capital T. Right, that means at capital T the capacitor voltage is given by capital T itself. Right. So now we are going to evaluate what will be the capacitor voltage in between capital T to 2t. That is for capital T less than t less than 2t. Right? That means capacitor is actually discharging from t volts. Right? As the current source is in opposite direction, it must be discharging. That means Vc equal to capital T minus integral capital T to small t dt. So that is capital T minus t plus t. So the answer is 2t minus t. Right? Again, at t equal to capital 2t, the voltage turns out to be 0. Right? Equation 2. Similarly, for 2t less than t less than 3t, we can evaluate the capacitor voltage. It is again charging from 0 volt. Right? That is Vc equal to integral 2t to small t dt. That is t minus 2t. But at t equal to 3t, it turns out to be 3t minus 2t. That is t volts. Similar to here. Right? This is expression 3. Right? Similarly for 3t less than t less than 4t, Vc equal to, right, it is from discharging, and it is discharging from capital T, right, capital T minus integral 3t to small t, right, dt equal to 4t minus t, and substituting small t equal to 4t gives 0, right, at t equal to 4t, right, at t equal to 4t, and I am marking this as expression 4, right. From these values I can plot a figure, right. I am plotting this, and this I am taking this as time axis. First one happens at t, so this is capital T, next 2t, next 3t, and next 4t. For small t equal to capital T, the voltage is given by capital T. So marking y-axis as capacitor voltage C. So up to this the value is capital T, right? Capacitor voltage is capital T. And at t equal to 2t, the voltage turns out to be 0. Again at t equal to 3t, the voltage turns out to be t. Option C indicates t u of t plus 2 sigma n equal to 1 to infinity minus 1 raised to n t minus nt u of t minus nt. So this turns out to be the answer, because t u of t is this function, right? T into u of t, and after that from t equal to capital T to tt, it decays. That decaying factor is given. Again t equal to ut, so it is again rising and again decreasing. This is alternating to sigma n equal to 1 to infinity minus 1 raised to n, right? So the answer turns out to be option C. All other options are not satisfying this wave shape, right? Now moving to a common data question. The following series RLC circuit with 0 initial conditions is given by a unit impulse function delta t. for t greater than 0, the output voltage Vc of t is, right? So we can convert it into S domain and evaluate these things, right? So I am plotting the equivalent S domain figure here. There is delta t converts out to be 1. Next inductor SL, that is S. Next resistance, that is 1. And next 1 by SC. So that turns out to be 1 by S, right? 1 by S. So the equivalent frequency domain or S domain figure turns out to be it in this way. This is Vc of S. This is Vi of S. Vi of S. Right? Now we can evaluate the expressions. Right? That is Vc of S, capacitor voltage to input voltage Vi of S, equal to, as it is a series combination, the current remains same. So I am not marking the current name. On the output side, we obtain I of S into 1 by S, that is 1 by S, right, divided by the total impedance, that is S plus 1 plus 1 by S, right. So multiplying both the numerator and denominator by S gives 1 divided by S square plus S plus 1, right. So now I can mark the denominator side as S plus 1 by 2 the whole square plus 3 by 4, right. S square plus 1 by 4 plus S plus 3 by 4, that gives S square plus S plus 1. The advantage I am obtaining here is that I can mark it in the form of sin omega t, right. Laplace transform of sin omega t is omega by S square plus omega square, right. So on the numerator side it must be root 3 by 2. So on the outside of this bracket I have to multiply by 2 by root 3, right. So taking inverse Laplace transform of Vc of t equal to 2 by root 3 sine root 3 by 2 t, but there is a shift to S plus 1 by 2, so there is a shift to, so e raised to minus t by 2, right. So checking options, answer 2 by root 3 e raised to minus t by 2 sine root 3 by 2, right. So option D. Now checking the data related question here, for t greater than 0 the voltage across the resistor is, in the earlier question we have to evaluate the voltage across the capacitor, now we have to evaluate the voltage across the resistor, right. So the expressions remain same except this expression Vc of S equal to 1 by S divided by S plus 1 plus 1 by S turns out to be, on the numerator side it is due to the capacitor contribution, now it is 1, right, 1. So I can write that thing, right, that is here it is 1. Now multiplying both the numerator and denominator by S gives S by S square plus S plus 1, right. Now similar to the last case I can split the denominator side, that is divided by S plus 1 by 2 the whole square plus 3 by 4, right. On the numerator side there is S, so I have to mark in terms of cos omega t. We know the Laplace transform of cos omega t is S by S square plus omega square. So comparing this expression to this expression I have to mark in terms of S plus 1 by 2, right. So there is a minus 1 by 2 to be provided here, right. So S plus 1 by 2 minus 1 by 2 divided by S plus 1 by 2 the whole square plus 3 by 4, right. Now I can split it into two terms, that is first term is S plus 1 by 2 divided by S plus 1 by 2 the whole square plus 3 by 4 minus 1 by 2 divided by S plus 1 by 2 the whole square plus 3 by 4, right. So this term turns out to be inverse Laplace transform as cos omega t, but for this term to be a sin omega t I have to multiply the numerator by root 3 by 2. That means I have to put inverse of root 3 by 2 here, that is 2 by root 3, right. Now the inverse Laplace transform gives this terms to be cos square root of this term, right? This is s by s square plus omega square, right? So square root of this term, that is cos of root 3 by 2 t, but there is a shift to 2, so e raised to minus t by 2, right? Minus 1 by 2 into 2 by root 3, that is 1 by root 3. So minus 1 by root 3. Now sine square root of this term, that is root 3 by 2 t into e raised to minus t by 2. So this is the inverse Laplace transform of this thing, and it is the final answer too. Now checking options, it turns out to be B, right? E raised to minus t by 2 is constant, right? E raised to minus t by 2 is constant. Cos root 3 t by 2 minus 1 by root 3 sine root 3 t by 2. So for more GATE tutorials, subscribe my channel. Now I am signing out till we meet again with another GATE paper. Thank you.